Welcome to Pomodoro Joe for Tuesday, September 19th, 2023. Today we're looking at LeetCode problem 287. Find the duplicate number. This is a medium problem. Given an array of integers, nums, containing n plus 1 integers, where each integer is in the range from 1 to n inclusive. Okay, what does this mean? This just means that we have an array of numbers that have the values from 1 to n, including n itself. There is only one repeated number in nums. Return this repeated number. You must solve the problem without modifying the array nums and use only constant extra space. Oh man, that makes it tricky. Okay, so we have an example, 1, 3, 4, 2, 2. It's easy for us to look at this and say, oh, 2's are duplicate, so we return 2. Same thing with this one, 3, 1, 3, 4, 2. It's easy for us to look and just see, but it's much harder for us to write an algorithm that will do the same thing. So let's take this simply. So let's put 25 minutes on the Pomodoro timer and we'll get started. So let's do the simplest thing we can think of first, and that's just to choose every number, compare it to every other number. So we'll take 1, we'll look at all the other numbers. Do we see another 1? We don't. Then we move on to 3. Look at all the other numbers. Do we see another 3? We don't. We move on to 4, so on and so forth. So let's do that. So some result. Set it to 0. Actually, I don't think I need this. Let's just do our loops. So for I in range, length nums. Actually, let me pull that out. Let's have num length here, or num count equals length of nums. All right. So for I in range, num count. And then for every j in range, and we'll just go from I plus 1. We don't need to compare the same number to itself. So we'll say I plus 1 to num count. Now we just compare the numbers at these indices. So if nums at index I is equal to nums at index j, then this is our duplicate and we return it. So we return nums at index I. Now I think we're guaranteed. Yeah, I think we're guaranteed that one of them will repeat. Otherwise, we might not return anything here. Let's just do this in case. Return -1, although I don't think it should ever hit this. All right, let's try this. Okay, so this works, but this is an O of n squared algorithm, meaning that I have to compare every number to every other number. So that's n times n comparisons, so that's n squared. So this probably won't pass all of our tests in the time that we need it to, but let's give it a shot. Okay, time limit exceeded. We pass 52 out of 58 of the test cases, but we just don't pass them all. So let's grab this test case and let's try another option. Okay, so this doesn't work. Now, one thing we could do is instead of going through every number, comparing it to every other number, we could use something like a dictionary or a set, just keep track of the numbers we've seen. And then if we see the same number again, if we check, is this in the set? It's already in the set, then we can return that number as being the duplicate. But the problem with that approach is this right here. It says our algorithm can only use constant extra space. Now, if we had a dictionary or a set or another array, those are all going to be not constant extra space. Constant extra space means that no matter how big this input is, we use the same amount of extra storage. So something like this count, that's fine. Now, if we were to use a set or a dictionary, now that set or dictionary will have to be as large as this input nums. So if we had 1,000,000 elements in our input nums, then our set would have to contain 1,000,000 elements, or our dictionary would have to hold 1,000,000 elements. Now, if this nums just had 2 elements in it, then our set or our dictionary would only need to hold 2 elements. So that is not constant. Those are varying. Those extra space requirements are dependent upon the input. So that is not constant extra space. So constant extra space just means whatever extra variables you use will not depend on the size of this input. All right, then another thought might be, well, let's sort the array. If we sort the array, then we can just go through every element and look at its neighbors. If their neighbors are the same, then we found our duplicate and we can just return that. But this also says we cannot modify the array. So we can't modify the array, and we can't have extra storage that is dependent upon this input size. So this suddenly goes from being like a medium problem to being a pretty tricky problem, like a medium plus plus problem. All right, so let's see, how do we actually solve this problem? So one way to solve this problem that uses constant extra space and doesn't modify the array is the fast and slow pointer method. This is something that you might be more familiar with in terms of linked lists and looking for cycles in linked lists. Now we can treat our array as if it were a linked list, and every element in the array just points to the next element that you need to go to. Because we know that every element in our array is an integer, and it's within the range of all of our indices of the array, that means we can treat the value of each element as if it were pointing to that index. So for instance, this 1 points to index 1. This 3 points to index 3. So we go from index 0, it says go to index 1, so we'll go to 1. Then that says go to index 3, so we go to 3. That's 0, 1, 2, 3. That takes us to 2. This says go to 2, so we go 0, 1, 2. And this says go to 4, so that takes us to here. And this takes us back to 2, 0, 1, 2, which takes us to 4, back to 2, and now we're stuck in a cycle. So we can use our linked list algorithm for fast and slow pointers to find this cycle. Then we need to find where the cycle begins by resetting our slow pointer back to the beginning. Then we advance both the slow pointer and the fast pointer along these loops. Now the slow pointer will eventually catch up to the fast pointer, and where they meet, that's going to be the index that represents the number that's the duplicate. That's the beginning of the cycle. So this is pretty tricky if you're not used to linked list problems and you're not used to fast and slow pointers. I would recommend, let's see, I don't know if I have a video on that. So I'll try to link something below on fast and slow pointers, and maybe I have a video, I don't know. I'll try to find something for you. All right, let's try this. So we'll start with some result. We'll set it to 0. We'll return our result at the end. Now this is probably not necessary, so let's actually not use that. Let me start over. Let's start with our fast and slow pointers. So our slow pointer will point to 0, and our fast pointer, well, it's going to point to whatever the element 0 points to. So that's nums at index 0. All right, so our fast and slow pointers will start at different places. Actually, no, I think I want them to start at the same place. Let me try this. Fast and slow pointers are both going to point to index 0. Now, while fast and slow are not the same, so while slow does not equal fast. Now the problem with this is they initially are equal, so we have to do something special to make sure that this loop actually gets run. So while slow doesn't equal fast, or slow is equal to 0. Okay, so we'll at least run this one time. Then we can say our slow pointer is just going to be the nums at the slow pointer. So whatever index slow is pointing to, we'll just go to that index, and then we'll go to that index the next time, and then we'll go to the next index, and then the next index. Now our fast pointer, we need to go twice as fast. So this is going to go to nums at nums of the fast pointer. Maybe an example will help here. So nums at slow, so they're both 0. So slow is at 0, it says go to index 1. So now slow becomes value 3 because it went to index 1. Now fast, it's also at 0. It says go to index 1, which is 3, and then it says go to index 3. So then we go 0, 1, 2, 3, and now fast is 2. Now eventually these two will meet. When they meet, now at this point we have to reset our slow pointer. So slow will be reset to the head of our list, or index 0. And now we'll just advance each one step at a time. So while slow doesn't equal fast, now we'll say slow is equal to nums at slow, and fast is equal to nums at fast. And then finally, when they do meet again, that's going to be the beginning of our cycle, which also is the number that is duplicated. So we can just return slow. All right, let's run this, see how we do. Okay, seems to work. Let's see if we can pass all the tests. And we pass. And we do pretty well. We beat 75% for runtime and 92% for memory. So yeah, we do great. Now we could probably clean this up and maybe, well, actually I know there's not a lot I can do to clean this up. Just use shorter names, I guess. What could we do? We might be able to start ahead of this 0, 0. Like this first loop, we might be able to shorten up. I don't really know. If we look at what other people are doing here, let's see what other people, what's the fastest solution? Okay, so they're using a counter. Now, this is questionable. I would say counter probably, most definitely will use some storage under the hood that will vary based on the input. So this is probably not valid. Let's see what else. It's clever, but not valid. A lot of these counters. All right, and this one's using a set, also not valid. Let's see. So this one's pretty clever. What they're doing here is breaking it into two problems, basically. So the first sort of subproblem is if you have just one duplicate, if you only have one number that's duplicated, then you know what your target value should be. So the target value should be this here, this n times n plus 1 divided by 2. This is essentially the sum of all the integers from 0 to n. So this is our target. This is what we should get. Now we actually get our total sum. We take our sum. We get the actual sum of the numbers in our array. So if we get the difference between our expected sum and the actual sum, then we actually check to see if that value is duplicated. And if we do, then we can return that value. This only works for single duplicated numbers. If that doesn't work, then we probably have more than one duplicated number. So in that case, they just go through and check. This is like the double loop that we did. I'm surprised this works, actually. All right, I'm spending too much time on this. All right, well, I hope this made sense. I know this one's kind of tough to follow, and this one really requires some visual aids to show you how we detect those cycles and then how we detect where the cycle starts. I just don't have the skills to do those kind of visual aids. Hopefully I'll find something else that can explain it for you, and if I do, I'll link in the description. All right, hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.